In this section, we're going to look at the basics of atomic structure, including how to write atomic symbols, isotopes, and how to calculate average atomic mass. As you probably know, atoms are composed of three types of particles: protons, neutrons, and electrons. The protons have a mass of about 1 atomic mass unit and a charge of +1. The neutrons have a similar mass, about 1 AMU, but a charge of 0. Both the protons and the neutrons are packed into the tiny nucleus at the center of the atom. The electrons orbit the nucleus and have a charge of -1. Electrons are much lighter than protons and neutrons. Their mass is only about 1/2000th the mass of a proton or neutron. So when figuring the atomic mass, we can pretty well ignore their mass. The electrons orbit the nucleus in what we call the electron cloud. So here's a question. What makes a hydrogen a hydrogen? Is it the number of protons, the number of neutrons, or the number of electrons? In fact, the number of protons determines the identity of an atom. As we'll see, a hydrogen atom can have more or fewer neutrons and still be a hydrogen. It can gain or lose an electron and still be a hydrogen. The content of its character, what makes a hydrogen what it is the number of protons. Since the number of protons determines what an atom is, we call this number the atomic number. This is really easy to see on the periodic table. The atomic number is the large integer number that's typically seen at the top of each entry on the periodic table. Another term we sometimes use is the mass number. The mass number is the combination of the number of protons and the number of neutrons in an atom. Note that this should also be an integer number. Typically, the mass number is not given on the periodic table. So what is this number below the atomic symbol? This is not the mass number. This is the average atomic mass. We'll show how to calculate these in a moment. So if the atomic number is the number of protons and the mass number is the number of protons and neutrons, is it possible for atoms to have the same atomic number but different mass numbers? That is, can you have the same number of protons but have a different number of neutrons? Yes, and in fact this occurs with most atoms. For example, there are three forms of the hydrogen atom. One has 0 neutrons, one has 1 neutron, and one has 2 neutrons. The first one, the one with 0 neutrons, is by far the most common. If we're trying to distinguish the hydrogen isotopes, this one is sometimes referred to as protium. The isotope with 1 neutron has a mass of 2, and so this one is referred to as deuterium. While the one with 2 neutrons has a mass of 3, this is a radioactive species referred to as tritium. Although these three have different masses, they're all hydrogen atoms, and so they will all behave in the way hydrogen atoms do. Sometimes we need to be able to show the atomic number and the mass number along with the atomic symbol. If we do, by convention, the atomic number goes in the lower left-hand corner. The mass number, on the other hand, goes in the upper left-hand corner. So, for example, helium has 4 particles in its nucleus. Its atomic number is the number of protons, 2. The mass number is the sum of the protons and neutrons, so we have 4 particles altogether, so we would show the mass number of 4 in the upper left-hand corner. Let's look at a couple of other examples. Number 1. The fissionable isotope of uranium has 12 protons and 143 neutrons. Show the atomic and mass numbers. Well, first off, we know that the chemical symbol is U. The atomic number is just the number of protons, and that's going to be written in the lower left-hand corner. The mass number is going to be the sum of protons and neutrons. 92 plus 143 is 235, and we'll write that in the upper left-hand corner. Number 2, show the symbol for a bromine atom with a mass number of 81. Again, we can write the symbol. If we want to write the atomic number, it goes in the lower left-hand corner. And if we want to show the mass number, it goes in the upper left-hand corner. Note that the number beneath the bromine, 79.904, is not the mass number. The mass number is the sum of the protons and neutrons. It will always be an integer number. So far, we've used the term atomic mass unit, but we really haven't defined what this is. By definition, one atomic mass unit, or AMU, is equal to 1.66 times 10 to the minus 27th kilograms. You really don't need to worry about remembering this number. You won't use it very often. Since atoms are so small, it's not practical to measure them in grams or kilograms. It makes things much easier to calculate their masses in AMUs, and we can generally use the mass number to give a good measurement of the mass of a particular atom. In later chapters, we'll talk about a more practical way to relate atomic masses in grams. So how do we calculate average atomic mass? Let's take a look at an example. Carbon exists primarily as two isotopes. Carbon with a mass number of 12 has a mass of exactly 12 atomic mass units. Carbon with a mass number of 13 has a mass of 13.0034 atomic mass units. About 99% of all carbon is carbon-12 and about 1% is carbon-13. There's actually a third isotope, carbon-14, but it's very, very trace amounts, and so we're not going to include it in this calculation. So how do we calculate the average atomic mass for carbon? What we're going to do is we're going to calculate this as a weighted average. That is, we're going to take the mass of each isotope times its relative abundance expressed as a decimal. So the average mass is going to be equal to the mass of C12 times its percentage plus the mass of C13 plus its percentage. And notice the percentages are expressed as decimals. So we would say this is going to be 12.0000 times 0.9893 plus 13.0034 times 0.0107. Calculating this out, we reach an average atomic mass of 12.0107 atomic mass units. This is commonly rounded to 12.011. And so that average atomic mass, the weighted average of the different isotopes, is what is shown in the periodic table. Here's a second example. Copper has two major isotopes, copper-63 with a mass of 62.93 and copper-65 with a mass of 64.93. The average atomic mass of copper is 63.55. Which of these is the closest estimate for the natural abundance of copper isotopes? Now, if we try to solve this mathematically, this is going to be a little bit detailed. However, we can estimate the value and come up with a solution pretty quickly. Notice that copper-63 has a mass of about 63. Copper-65 has a mass of about 65. However, it says the average atomic mass is 63.55. I'm just going to call it 63.5 for the average atomic mass. So, which of these answers makes sense? Would it be 10% copper-63 and 90% copper-65? That would make the weighted average almost 65. That can't be it. What if it was answer E? What if it was 90% copper 63? Well, then it would be something like 63.1. It would be almost 63. That can't be it. Look at answer C. If it was 50% copper 63 and 50% copper 65, that means we'd have the same amount of 63s and 65s. This would be a mass of 64. We're not at 64, we're at 63.5. So with our mass of 63.5, we have more of the 63s than we do of the 65 by about a 3-to-1 ratio. For example, we could say if we had 3 63s for every 1 65, that would average out to 63.5. The closest approximation we have there is answer D. 70% copper 63, 30% copper 65. So, in conclusion, the identity of an atom is determined by the number of protons. This number is referred to as the atomic number for an atom. The atomic number can be located on the periodic table above the symbol name. The number of protons and neutrons together is referred to as the mass number. Atoms of the same type with different numbers of neutrons are called isotopes. The mass number is typically not given on the periodic table. Rather, the periodic table shows the average atomic mass, that is, the weighted average of all the isotopes of that atom.